All right, thank you very much. And today I'm going to be talking about avoiding nonsense that we're faced with when we deal with these AI systems these days. So the goal is to stay away from this nonsense. Oh. Sorry, it's kind of hard to avoid. And here I am, right in the sun. OK, so I was expecting the projector to be a little lower. Anyway, it wasn't quite a fight. All right, so why do we want generative models? You know, as our computers get smarter and smarter, they're able to answer questions, caption images, translate things, make poetry, all kinds of things. They can even make images and things. I'm not going to talk about that. But the standard approach for training generative model is to maximize the likelihood. You take, say, n independent samples of data, and you try to maximize the probability of these things, which is equivalent to minimizing the sum of the negative logs, the log loss. Okay, and then you generate from that distribution. But as many of you known over the years, you've played with AI systems, you generate nonsense. In this talk, let's just think of a simple example, like you're trying to generate some text. Sometimes there's in translation, you have a sentence that you want to translate. Sometimes you just want to generate stuff. They're very similar, but let's just think about the pure generation case here, where we would just want to generate future examples from the sentence, but the other case is related. So, let's take a simple case of generating LaTeX articles or even LaTeX math formulas. You know, you get a bunch of examples of LaTeX math formulas, and then if you train a maximum likelihood model, it depends on the kind of model, but if you train a simple model, like what's called a Trigram model, where the probability of each character is based only on the previous 2 characters, then you'll get nonsense. And here the algorithm generates a backslash, which is fine. It generates ET, eta, and then it can only look backwards 2 characters. It sees the TA and thinks maybe it's a tau. And you get nonsense, and you guys are used to this kind of stuff from relatively simple models. Can we do better? Okay. And can anyone think of a different kind of trigram model that would never generate nonsense? Just a probability for each character based on the previous 2. That would always generate LaTeX formulas that compile. Output nothing, an empty formula that would work. What is it? Space? Space. Sure. That would be valid. Talk about something more interesting. I'm just trying to wake people up. Numbers, good. You could just output digits. That would give you valid LaTeX, right? And you could capture some fraction, some small fraction of LaTeX formulas out there. You could actually generate formulas like this with a trigram model too. You could, but good, very good. Okay, or you could use deep learning, and then you could use maximum likelihood over deep learning, and you would probably get deep nonsense. And there's a bunch of examples like this on the web, and people are very happy with their models, and they look somewhat sensical, although they are also nonsense. I mean, first of all, they may not even compile. So this was trained on Wikipedia, and the parentheses don't even match. Come on. And they were very happy. So that's nonsense in a very clear way. But they were very happy that it generated this URL. But this URL is not even an existing URL. What if we want to be an existing URL? I mean, come on. Or if you look at the English, that's really not sensical. It's sympathetic to be to the. So. Anyway, so we want to generate sensible stuff. So if you focus on the simple examples, you can often find simple models that will fit the simple examples. Just like when a human learns a language, right? If somebody is learning English for the first time and they're trying to write a Wikipedia article, they would write with simple, short sentences. Just because the other Wikipedia articles they read are complicated and have long sentences, they will do that, and that's kind of what we want our machine learning algorithm to do. Maybe it'll start with something very simple. Maybe if it's ambitious, it will add a hyperlink to something that it knows is in the corpus. Okay, so that's what we're going to talk about this talk. These guys actually do have a lot of nonsense, but anyway. So why do these generative models output nonsense? The reason is because, one reason is because the true distribution that they're looking at for data is not in whatever class that they're fitting, right? That's a possibility in the trigram example, right? The LaTeX formulas are not generated by trigram models. Another reason is that they fail, maybe use some general model like neural nets, which you can encode any circuit, and it probably could encode a lot of things, but maybe they fail to find the best one in the class. Maybe they don't have enough data. So I mean, I could give you a distribution, a model which is just the class of all distributions. That's very general. It includes that, but you can't learn it. So there's not enough data to learn that. So those are 3 different possible reasons why we might be getting all this nonsense, and how are we going to avoid it? Okay, so what is the model? So we assume we have as many polynomially as many samples as we want from real data, from the distribution over X. And then we have an oracle to the nonsense set. So we can ask, is this sensible or is this nonsense? Okay, and I'll talk about that in a minute. And then we're given some family of distributions, okay, Q. And our goal, our goal is to find the best Q with the following properties. And this is the most technical slide here, so don't worry. There's not going to be a lot of math other than this. So there's this nonsense set N. Our goal is to output a Q hat which assigns probability epsilon to nonsense. That just means the probability assigns to nonsense set is at most epsilon, so it almost never generates nonsense. The expected loss, think of log loss, but I'll clarify in a second, it has to be a bounded loss. The expected loss should be not much bigger than optimal, where optimal is the minimum, the best model that never outputs nonsense. So we compare ourselves to things that never output nonsense, and we want to achieve as good a loss, as low a loss as the best that never outputs nonsense. So we have a little bit of leeway here, epsilon 1 and epsilon 2. Now this is actually not achievable, it turns out. You can prove, and we prove it's not hard, that you can't do this, unfortunately. But there's one small change you can make to make this possible. Does anyone want to guess what that change would be? Anyone guess? What is it? That would be interesting. Maybe we could have an extra constant or something. Maybe we could get something. That's a good idea. The trick is that we can just do improper learning. So if we don't force ourselves to output a model in the family, then it turns out we can't solve this problem. Information theoretically, okay. We can say something about polynomial time, but let's not get into that now. So basically, we can find a Q hat, a probability distribution not in that family, in time, or sorry, not time, the number of samples, which is polynomial in either the VC dimension or log of the size, and 1 over epsilon and 1 over epsilon 1 and 1 over epsilon 2. Okay? Oh, our lower bound is information theoretic. Yeah, it's not hard. Good question. And okay, what do we need to assume about the loss? Well, we actually need to assume we have a bounded loss. So log loss is unbounded, but we need to assume we have a bounded loss. So you could just cap your loss, log loss, or you could move it over, which is called smoothing. It's something they do in language modeling often. So just as an illustrative example, suppose you had data that looked like this, and you were trying to learn it with rectangles. Okay. So if you were trying to minimize your log loss, you would have to cover all the data, because if you assign 0 probability to either of these 2 points, your loss would be infinity. And so you would end up with this terrible rectangle, and if you generated from it, that's maybe not a good fit. I mean, it depends on what the data is or what's generated from, but it's probably not what you mean. If you have a bounded loss, you can say, okay, I give up on these 2 points, I pay something for them, but the minimum bounded log loss rectangle, or minimum bounded loss rectangle might be something like that. Okay. But unfortunately, the rest of the stuff is nonsense, okay? And so we have an algorithm that will somehow try to approximate the best rectangle, or do as well as the best rectangle, that doesn't generate nonsense. And in the interest of time, I'm just going to skip it, but it's kind of fun, and come to the poster and we'll tell you about it. That's the algorithm. Just the last point, I guess, to make is that the nonsense oracle can be non-deterministic. It really can be a human-based thing, because it could be, we're not making any assumption about it. We're kind of agnostic to it. It could be different people, and it could be randomized and stuff like that. So I think it's pretty general. And the conclusion slide we made with a new technology which generates slides. We call it Deep Slide Hallucinating IT. And let's see, here it is. It now has GANs. It's pretty cool. And so, it's not bad. If you're willing to use the old technology, you can end up with high quality stuff like this. That's it. Okay.
Are there any questions? Yes.
Oh, it's active in the sense that we're making queries to ask what's valid and what's not. Yeah. Okay. So the question is, how are we being active? And the answer is, well, we pick a rectangle, or pick a concept from our class, and then we start generating samples from that. And if they're all valid, we're great, we're just done. But if they're not valid, then we say, okay, we need to generate a further function distribution from that class, which never generates any of these invalid points. So we keep track of a list of invalid points, and we make sure we never generate any of those invalid points. The validity oracle is just, is this point valid or not? Yeah, we keep generating consistent concepts from the family that consistent with all the data that we've seen so far and that minimize our loss. And then we generate random samples from those and query those points.
I think in the interest of time, I'll just thank the speaker again.